कर रहे हैं आप?
हाँ हाँ, श्योर श्योर।
यस सर। सर मेरी ना एक और मीटिंग चल रही है साइड बाय साइड, तो अगर इन द मिडल मैं रिप्लाई ना करूं सर, तो
नो
आप
प्रॉब्लम।
टेक्स्ट कर दीजिएगा, मैं इधर रीड कर दूंगा। ओके सर,
श्योर।
थैंक यू सो मच सर।
Good evening, everyone.
गुड इवनिंग सर।
Good evening, sir.
So, anybody has any doubts, please bring them up. So last week in Bangalore, they had a Vision Summit. That is the India Electronics and Semiconductor Association. They have an annual thing called as Vision Summit. So I was there for some time, and there were a lot of exhibits. Mainly because I think, as I told you last time, see, because India is getting into this manufacturing, right? So you may have heard that in day before yesterday in Gujarat, Prime Minister inaugurated Micron's assembly unit, right? So in the same way, you can expect by end of the year, maybe even Tata will set up their fab and ready to. They're expecting that by end of this year they will be starting production. So like that, slowly a lot of players are getting into the market. So this was evident in that exhibit also. A lot of companies were exhibiting. So companies which are trying to be in the either manufacturing or testing. So as I may have mentioned to you last week, so in the past 40 years, there has been no emphasis on manufacturing in India. It's been mostly design. So jobs were mostly in the area of either digital design, analog design, design verification, analog verification. To some extent, you know, there may have been some jobs in validation, but now there are possibly going to be many jobs in the manufacturing also, test and assembly, packaging. So you can expect many jobs to come up in the next 1, 2, 3 years, and possibly it will sustain also the way things look, right? And I think they're expecting. They have established, I think, several skill generation programs because the need is, immediate need, right? You have to recruit right away a bunch of people. So this is a good opportunity. So we have used words like verification, testing, validation. I hope everybody is clear about those three. If you have any doubts, ask me. So there is verification, there is testing, and there is validation. Anybody has any doubts on these three? What they mean? Anybody wants to explain what is verification?
Sir, validation is happens before silicon takes place, or before in physically we come into the factory, on only in designs. Then characterizations and verification happens after the silicon uh, is in the room,
Okay. No, no. There is a
when
small
we have
error.
to manufacture
No, no,
the
no. No, 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 no. Just a minute. I think you are saying the right thing, but you are using the wrong words. See, verification happens before silicon. So verification is the step that is done immediately after design. Okay. If I call you and give you a specification and say I want you to design a circuit which does the following, then you will interpret it and then you will go and design something. There is a possibility that you misunderstood my specification. So there may be a bug. So we have to verify the design. At this stage, there is no silicon, right? We just want to verify the intent. It's something like you have given me a sort of a, see, for example, if we are publishing a book or something like that, see, we may have in our mind what this book should be all about. We have told several authors, they will all contribute different chapters and so on. So we put everything together. At this time, there is no book yet. It's not been published. It has not been printed. It's just a PDF or something like that. So we still have to go and read that online PDF to see if there are any errors, right? Maybe there are errors such as typing mistakes may be there, or factual errors could be there, or grammatical errors could be there, wrong, uh, you may have seen sometimes figures are overlapping, all kinds of things may have happened. So we had to go and verify that PDF to see if it is going to be all right? So that is what is called verification in design also, because people may have made mistakes when putting everything together, right? See, today nobody designs from scratch. Okay, it's gone, because the complexity of the designs that we have today is very high. So you can't do it like the way people used to do earlier, design everything from scratch. That's all gone. So we put things together. So we may have somebody giving us a microprocessor, like ARM company is there, which sells microprocessor IP. Then somebody else like Synopsys or Cadence may be selling an IP for some peripherals like USB controller and so on. We may also purchase memory IP from some other company, right? So we can take CPU, memory, peripherals, everything, and we can put them together. So when you put things together, you may make mistakes, right? You may have connected things wrongly, right? If you have ever built a circuit on breadboard, you know that sometimes connections can go wrong, right? See, for example, the bus may be numbered from 7 to 0. So 7 is the most significant bit and 0 is the least significant bit. And memory also has another bus. So we have to make connections. And we may end up connecting it wrongly, right? 7 is connected to 0, 6 is connected to 1, and all that, some we misunderstood. So that is a bug, right? And fortunately, at this stage, we are still, we have not gone ahead and made any silicon. So we can simulate and verify if there is any bug, and we can go and debug it. Right? We can fix this. we can fix our specific implementation. We can fix the design. So that whole thing is called as verification, and it takes a lot of time. Okay. So a bunch of people, possibly hundreds of people, are usually busy doing verification if the chip is large. So once verification is complete, we continue with the rest of the design. See, at this stage, we have only done what is called as functional verification. We have not yet actually designed anything with transistors and so on. It's all in Verilog or something like that, right? So there are tools available today which will take this Verilog written in a high level language like RTL, register transfer language, and they can compile that, okay, into gates, right? And the gate level design can be further translated to the transistor level design, and the transistor level design can be converted to the actual rectangles, that polysilicon, diffusion, oxide. So that is a VLSI design flow. Okay, tools are available today to do all of this, and usually tools are correct by construction. Okay, they have been tested quite a bit, so we don't expect the tools to make any errors when they go from the RTL to the final layout, right? But yet, at the end of every step, people do some simulations to make sure that there is nothing seriously going wrong. Okay, so we keep doing some little bit of verification at the end of every transformation, maybe from RTL to gate level to transistor level to the layout level, etc. People keep running certain tools to make sure that there are no bugs, no unintended errors. So now we have gone all the way to the layout. So this can be now shipped to the manufacturing a site. The manufacturing may happen elsewhere. So we call that as tape out. Okay, tape out means the shipping of the files. Okay. Once upon a time, people used to send it on magnetic tapes because they were very large files. You could not fit them on. In those days, hard disks were not very big, so people used magnetic tapes. Today, nobody uses magnetic tapes. It is still sent on hardware. In fact, it may go through internet. People may just use tools like file transfer protocol, etc., to just transfer it over the internet. And once again, we trust that the internet will take it safely without any errors, right? So the files are now sitting at the manufacturer's end, and they use these layouts to generate what are called as masks. So typically there may be 12, 13 masks that are required to fabricate all the layers that are required. But when we do all this manufacturing, things can go wrong. Okay, we did not intend any. These are all verified. Everything has been verified correctly multiple times. But during manufacturing, each chip may have different defects. So in one chip, maybe there are some impurities in the silicon. In another chip, maybe there is some surface imperfections in the silicon. In some other one, there may be a dust particle or something like that. So every chip will come out differently. Okay, it is something like see, suppose there is a baker who makes a lot of cakes or cookies or something like that, right? Verification is like that person has a recipe, and he or she has perfected the recipe, made sure that it's all going to work, etc., right? Now they are actually manufacturing. They are actually mixing the dough and sugar, whatever it is, and they are actually, baking it. Okay? At that time, as you can imagine, things may go wrong. Some cookies may break. Some may have more, whatever. Some ingredient may be more in one thing or whatever. Right? Every cookie is likely going to be different. Okay? Even if it is manufactured with a lot of automation, right? So if you go to an actual cookie factory or biscuit factory, they have automated everything, right? But in spite of it, when they come out, the cookies, manufactured cookies, you can watch videos if you want. There are plenty of these available on YouTube on how these are manufactured and fully automated. You can expect that there will be some defects, right? Some cookies may be broken, or some packaging may not be good. See, they use automatic packaging also, right? Paper with all the information printed on it is going to come, and it is packed. They are assembled. I mean, they are sorted into. So suppose 10 cookies are there in every package, so they will sort it, right? And then packaging, it will be packaged, right? So things can go wrong. See, maybe in one of them there are less than 10 cookies. So finally, you are supposed to test each one of them, right? So imagine billions and billions of cookies are packets of cookies are coming out. Each one of them has to be tested. Okay? Whether cookie manufacturers do that, we don't know, because see, the cost of that package, that packet of cookies may not be so high. Okay, so if somebody comes and complains that your cookies, there is they are broken or something, that guy will just replace it for you. Okay, he will not ask any questions. But in semiconductor, see, those chips are very expensive, right? Some of these chips may sell for your look at chips that Nvidia sells today, right? AI chips, right? I think they are selling for a few $1,000s a piece. So imagine each chip is a few $1,000, and you supply a bad one because you didn't test it sufficiently, right? So customers are not going to be happy about it. And if you have returns, if customers start returning the chips, it's going to actually hurt you badly, right? You will have to, the whole thing, becomes a big overhead. So that is why you have to test the chips before you sell. So the verification process is done before manufacturing. The testing is done after manufacturing, and testing is done on every chip that comes out. The word validation is used before we ramp to production. See, it's not that, when we send the design files finally to the manufacturer, that guy is not going to start manufacturing in millions right away, okay, because it's a little bit of a risk. So that person will initially make only a few, okay, because they want to know whether the manufacturing process is all right. Okay, they may make just a few chips, and then these are subjected to a great amount of testing. Okay, they are tested, very thoroughly. They may even make a small PCB, inserting that chip into that PCB, writing some software, and checking whether it does whatever it is supposed to do, whether it gives the performance that it is supposed to give. So this is a very heavy duty testing. Okay, we can't afford to do that kind of heavy testing for every chip that we are manufacturing. Okay, because that validation of every chip, it may take several engineers to do many weeks. Okay, they will sit in a lab, they will use all these expensive equipment, right? They'll observe waveforms on the oscilloscope, they'll take measurements, They'll vary temperature, they will vary voltage, they will check how the chip responds. It's all a lot of work. And then that information is used in creating what is called the data sheet. Okay, when people sell a chip, they will also sell a data sheet with it. Right? In that data sheet, it will say what is the expected gain, what is the expected bandwidth, how much it varies. All those things are written there. So the validation engineers, they are the ones who help in building that data sheet. They apply a lot of testing. Okay, lots of measurements, and they have to repeat it on every maybe chip for about maybe 10-15 chips. Okay, because every chip is different, right? So one chip by luck may be giving you a very high bandwidth, another may be giving you slightly less. Okay, so you may have to repeat and take some sort of an average and all that. Right? So that is what the validation engineers do. And once they feel that it is okay, see, if they feel that it is not okay, they will reject it. They'll say, this, don't mass manufacture this chip, it's not going to work. Okay, this is not acceptable. There is something wrong in this manufacturing process, or there is a bug in the design, or something is not right, and as a result this will not fly. So then it will go back. Okay, then maybe if there is a design problem, we have to fix it in design. If it's a manufacturing problem, we have to fix the manufacturing process. Then again they will go through one more iteration. So this is a highly iterative process. So finally a time will come when they feel that things have stabilized, all the problems have now been sorted out. So now we are ready to do mass manufacturing. It is something like, to give you the same analogy of a bakery, see, maybe you have come up with a very fancy 7-layer cake or something like that, right? It's a very complex manufacturing. Okay, but you know that there is a big market for something like this. So you have designed the whole thing, simulated it, and made sure that all these cakes can be baked and assembled, and fancy something will be done. But then when it is manufactured, 1 or 2 samples you will make, and you may realize that there are some difficulties here. You'll fix all those things, and finally you will get to a stage where you are confident that you can make many of them, whatever number of whatever is your demand, right? So that is so there are 3 terms we use. Everybody understood? Verification, validation, and test. Is that clear now?
Yes.
Yeah. So you can see that there are different 3 kinds of jobs. So there are some people who work on verification. Those guys are good at Verilog, right? They are good at system Verilog. They write test benches. They are not, they don't know how this chip is manufactured. That is not their world. Their world is more of Verilog, system Verilog, and all that. They may never ever step into a manufacturing site, etc. Whereas those guys who do validation, they live in labs. So they are, most of the time they spend in labs. Their job is to maybe design some PCBs where these chips are inserted, and some software may be written, and then they will plot the waveforms, print the characteristics. Okay, so that is what the validation engineers do. So they should be good at instruments. I mean, they should be good at using the instruments and so on. Those who get into testing, they are usually, they are right next to the facility where manufacturing is done, right? So they may actually be spending their time in the manufacturing unit itself. And their job is to use the testers, and they should know how to use the tester, how to optimize the test programs. See, because how do you test a chip, right? See, suppose I give you an AND gate and I want you to test. You may say, let us exhaustively test it. Let us apply every test vector to the AND gate, and we can see whether it behaves according to the that truth table of the AND gate. But if you are designing a very complex microprocessor or some such chip, then you can't do that. Right? You will need lots of tests. And see, if you start applying so many tests, then you will not be profitable. Right? It will take so long to test each chip that it is not very profitable. Right? Imagine, you see your IIT Madras also gives you tests, isn't it? They conduct maybe 2 or 3 tests for you before they decide to give you a grade for the whole course, right? See, you can argue that to understand whether the student really understood the subject, we have to give very long tests. Maybe I can be very ambitious and create a 10 hours of test. It will be very thorough. I can test each one of you very well. I will ask every question possible to see whether you have understood every concept I have taught you. But it doesn't work like that. Okay, 10 hours of testing per student. It's impractical, right? It's too expensive. So we have to reduce the amount of time for testing. Right? So we are only giving you, I think, in the entire semester, 1 hour quiz 1, 1 hour quiz 2, and then 1.5 hours maybe final exam. Right? And if they are carefully chosen, if the tests are chosen very carefully, then that is enough. After all, we have to just separate the students into some bins. Some students, we consider them as A, that means they understood the subject very well. Then there are some who are B and C, and so there is some sort of a grade that we have to create. In the same way, chips may also have to be graded. So there are some chips which are so good that they can be sold for very high profit. Then there are some chips which are, they may not be as high in performance, right? So they are sold to the next profitable market, and so on. So we may create several bins like that. So that is how testing is done, and we have to optimize the time it takes to test. So I may have explained this in the videos also. See, let us say I have bought a very expensive tester. Okay, the tester will usually cost in millions of dollars, right? And at one time, it may be able to test a number of chips. See, many times on that one tester, maybe 64 chips or something like that can be tested at one go, which means the tester requires a lot of memory to store all those tests, right? And it has to be brought at a high speed. If you are going to take a lot of time to just set up the whole test procedure, etc., every microsecond or millisecond will count. So the testing has to be fast because we have a lot of chips to test. See, in your class, there are about maybe 50, 60, whatever, 70, 100. So I can't ask the grader to give a very thorough test to all of you and say you go and grade all of them. Not possible. So that is why we are resorting to automated things, right? So you have multiple choice, right? So we have simplified many of these things. So in the same way, the test engineers, you may give them a number of tests. Okay. So if you know how JEE and all these tests are made, See, final JEE paper may contain a certain number of questions, but they would have gathered questions from a number of places. Okay, many professors would have made those questions, and finally they will select. Okay, so the test engineers in a way are doing that. Then they are also responsible for actually applying the tests and you know stamping the good chips as good and ready, getting them ready for shipment. Then what happens to the bad ones? Okay, I may find that some small percentage of my chips are actually not good. Okay. So of course I cannot sell them. Okay, I cannot do anything about them. I have to throw them away. But before throwing them away, maybe there is something that we can learn from them. So we'll understand what is the reason why they are failing. So just like if some students are failing in an exam, so suppose there is a class with 100 people and let us say some people are failing in that examination, then naturally, the college or IIT will be worried as to why there are some failures. They will go and investigate what is going wrong. And then some correction has to be put in place. So that is called as diagnosis. So that is very expensive. Usually students don't get those jobs. Okay, so you don't have to worry about diagnosis at this stage. If you spend maybe 10-15 years in this testing job, then one day they may you may get a job in diagnosis or something like that. So it requires a lot of experience, and very senior people only go and diagnose. So they will be able to use various techniques to guess what could be going wrong. Okay, so that is why I said it is very lot of experience is required. So if I buy a very expensive tester, let us say it costs $1 million, unfortunately these testers, they will become outdated soon, because the manufacturing keeps changing, isn't it? You have seen in VLSI, the technology tends to change often. In the early days of VLSI, I think Moore's law predicted that every year the density will double. So every year the equipment had to change. But now it doesn't happen every year, but it does happen every few years. So you can imagine all that expensive equipment that we paid for, it is not going to be used anymore. So you may have to sell it away to somebody else. Maybe some other person is willing to take that, right? So there is maybe you bought it for $1 million and you are going to sell it away for $100,000. So essentially, $900,000 was the essential money you paid, and you used it for a certain number of years. Okay. Let us say you used it for 3 years. So how many chips can you test in that 3 years? See, you cannot continuously use it, right? Maybe the holidays are there, etc. So you will have to make room for those things. Plus, maybe there are some downtimes. Maybe the tester develops a problem of some kind, so it may have a downtime. So you subtract all that and then see how many days of actual productive time you get on the tester. Then you assume how much time it takes to test a particular chip. Suppose it turns out that it takes about 10 seconds or something like that. So you can do some arithmetic. Okay, so if each chip requires 10 seconds of test time, then and out of 3 years, 3 times 365, take away all the holidays and downtime, etc. What is the number of hours left and how many seconds, and then you will get the math on how many chips that we could actually test. And that is what we need to maximize. We need to get good value for the machine that we bought. It's a very expensive machine. We are spending $900,000 totally, right? So the cost of testing is that $900,000 divided by whatever number of chips that you were able to test. That is the test cost, right? And who is going to pay for the testing? The customer has to pay, right? You are not going to, so the customer will have to pay for that cost. So if your chip is actually, what are the costs with a chip? One is the manufacturing cost, okay? That is the cost of all the silicon, all the materials that go into the chip, copper, and so many things are, silicon, copper. Then the cost of manufacturing, that means all the machines that you have invested on, the electricity cost, everything. So all of that has to be accounted for in the manufacturing cost. See, that is also, a certain significant part. Then the design cost. Okay, you are paying very fancy salaries to all the design engineers. Maybe they have worked for about 5 years. Each of them has to be paid a certain salary for 5 years, and you have to invest, maybe several hundred people are involved. Okay, then you have to have the, tools, electronic design automation tools are required. You have to license those expensive tools. Then you have to have offices. All of it will be a design cost. So there is a design cost, manufacturing cost, and there is test cost. So the design cost, if you design a chip, and let us say you manufacture in a large number, okay, this chip is so popular that it remains very popular for many, many, many years, okay, then the design cost becomes, it's a one-time cost. The more chips you make, the design cost is, divided by that number of chips that you are selling. So suppose I have spent, let us say, $25 million on the design. And suppose I end up, selling about 100 million of these chips. So $25 million divided by 100 million, right? So it's because of the denominator being so large, the design cost doesn't look like a big amount. Okay, it's, in this example, I think it is like $0.01 So the secret is you should have such a large market. If the chip comes and let us say it is not going to stay for a long time, competition comes in, and this chip is no more looking attractive, then unfortunately design cost you could not recover. So design cost is one aspect. Then manufacturing cost, that is always going to be constant, right? If you make more chips, it will cost you more. Okay, unlike design cost, which begins to look smaller and smaller if you make more and more chips, manufacturing cost cannot be like that. If I make more cookies, I need more dough and more sugar, more all of those things. So I will need to spend. Now, what about test cost? The test cost is also unfortunately similar. The more chips I make, the more will be my test cost. Design cost is not like that. I hope everybody is clear on that.
Yes, sir.
So test cost does not scale down as you make more and more. So what can happen is, see, suppose there is a chip See, when a manufacturer makes a certain chip, they are supposed to produce that for a certain number of years. See, because I may have a customer who has started using the chip, and I realized that initially about 25 customers were buying my products. Now only two in the world are left who are using that. Everybody has moved to some other more, better products. I myself have better products. Okay, my company is only making better products. But these two guys are hell bent on using the old one. Okay. They are not interested in upgrading because they are a small company. Okay, they buy some small volume, but they are they don't want to migrate to a different design, etc. And for their sake, we have to continue to manufacture. We cannot put a stop and say no. In future, we are not going to make this. Okay, so the companies tend to give an advance warning. So suppose we have decided to stop manufacturing this chip from 2028, then we have to give them much early advance notice, saying that this is going to happen in 28. You better start moving to a different technology or a different design. So in that period when we are not making much profit, there are very few customers buying. Unfortunately, we are still spending a lot of money on testing these chips. Okay. The volume is very small. In that situation, it can actually be very counterproductive. Okay, so this is something that manufacturers would like to avoid at all cost. Okay. So if the chip doesn't really pick up, they would like to see whether they can avoid having to manufacture it, for the sake of a very small number of customers. Okay, so so you should understand what these costs are: test cost, then design cost, and manufacturing cost, and so on. So the goal of the test engineer is to reduce the cost of testing. Okay, so your NPTEL office, they are the ones who administer the test. So if I give them a very large, lengthy test and say, no, I have designed a 3-hour test which thoroughly tests every student, they will not listen to me. They will say, no, sir, it doesn't work like that. You have to reduce it to only 1 hour. Okay. So how do we, reduce the test cost? And how do we produce tests which still are able to find all the defects? So if my test is insufficient, suppose I don't test them enough, then what can happen is, unfortunately, bad chips will go into the customer's hands. If I don't test it enough, right, then my quality has come down. Okay, I'm selling away bad chips to the customers, and that will backfire on me later. Right now, I'm happy because I have reduced the cost and I'm very happy. Right? If, for example, I could have an extreme and say, I don't want to test at all here. What is there? Why should we test? We have a good production. Everybody is good here. Manufacturing is very good. Right? Why should we bother? Right? Anyway, I never see many people complain. So let us not test at all. See, we can become like that, right? IITs can say, hey, JEE is such a good exam. Very bright students are entering our IIT system. Why should we conduct tests for these guys? They're all good. Like that, we can take a stand, right? But that will backfire on us, right? It will not work. So in the same way, we had to watch out for quality, which is measured by defective parts per million, right? I think I may have mentioned it in the last class, right? So if I sell 1 million chips to my customer, then the customer will look at the number of defective pieces that I supplied. they have made a contract with us that up to 100 is okay. But if I start supplying more than 100 defective parts because I'm not testing enough, then they will come back to me and they can ask for replacements. Okay, so that is going to hurt me badly because now I have to make more chips just to replace the bad ones. So quality has to be controlled, which means I should not allow any bad chips to escape. So what is a escape or a test escape means? I somehow allowed a bad chip to escape from my scrutiny. The test was not very solid. It allowed some bad chips to escape. So now the question is, how do you find all these tests? So which are these tests? So if I ask you the question, how do you test a microprocessor? A number of you will think of, let us try to write some software, right? Many of you may say, hey, let us see if the add instruction is working correctly, the subtract instruction is working correctly. See, if you start thinking like that, you can imagine how many functional tests I had to write. These are called functional tests. That means, does the microprocessor do its function correctly? It is adding properly, it is multiplying properly. If you suppose there is an instruction called add R1, R2. Okay, in ARM, for example, there is an add instruction. Add R1, R2, R3 means, take the sum of R2 and R3 and put it in R1. Now, if there is a defect in the microprocessor, the add instruction may not work at all. It is not doing add correctly. Okay, or it may be, instead of add, it may be doing something else. Okay. Or instead of adding R2 and R3, it may be adding some other two registers. Or instead of putting the result in R1, it may be putting somewhere else. Or it may be putting it in more than one place. Anything can happen, isn't it? So testing that add instruction itself can be a nightmare, because after addition, you have to verify that only that register R1 is updated, nothing else is updated, and indeed R2 and R3 are correctly added, right? So you have to make sure that the other registers contain some other values, so that I'm not going to confuse that. I had to be confident that only R2 and R3 are getting added and R1 is being updated. So a lot of work will have to be done to create this simple test. So you can imagine in a functional testing of a microprocessor, it will be very, very, lot of tests will have to be written like this. So today, unfortunately, that won't work. Okay, our modern processors are too complicated. Modern ICs are too complicated. So nobody does functional testing really. We can't afford to do that. You understand, no? So functional testing is not done. In software, they still do functional testing. See, if you have to verify that there is a C program which is working correctly or not, we still sort of rely on functional testing. But in hardware, it's not possible. Okay. So what they do instead is they go in for structural testing. So we will go and look at the microprocessor and say, hey, how many wires are there in the circuit? How many nodes are there, right? Let us make sure that none of them are stuck at 0 or something like that. So I may have a lot of wires. Because of some defect, maybe some wire appear to be stuck at 0. That means it is always 0. It doesn't change to 1 at all. Or some wire is permanently, it appears to be stuck at 1. There is some defect which is causing it to behave like that. Or some memory cell in the memory of the processor. See, the processor has registers and other memories, right? So maybe some memory cells are stuck at 0 or stuck at 1. Or there may be some coupling happening between memories. See, maybe I write into one memory location and that is changing something else somewhere else. Can you imagine that? I try to update memory location 55 and silently some other memory location also got corrupted. Okay. So these are all the possible faults that can occur. So what is the difference between a defect and a fault? A defect is the physical mechanism. Why is a node stuck at 0? Why is it stuck at 1? If you want to understand a defect, you have to go down into the transistor level circuit. You may even look at the layout and see, what went wrong in the layout, which is causing this behavior. Okay. We don't have time to do all that. Okay, I am not willing to go into defects. Okay, just like, see, if we notice that a number of people are failing an exam, see, then we start asking, why did they fail? What happened? Why, that was the student not in a good mood, or why he's not studying? All kinds of theories we'll have to start investigating. Right now, you can't really do all these things. Okay? If there is a person willing to spend a lot of time understand that, they may be able to correct some teaching method itself. They may say the reason why this is happening is because the classroom is has an audibility problem. Okay, when the professor speaks, nobody is able to listen correctly. So that may be the diagnosis. Then they will correct the issue. Okay, that may help in. So that is what is required to be done at a certain stage. The diagnosis is something the experts will actually figure out. But the manufacturer at this point of time is not interested in diagnosis. He just wants to remove the bad chips and sell the good ones. That's all he's interested in doing. And he wants to do that very quickly. He doesn't have the time to apply a lot of tests. If you say for your microprocessor, I have come up with 100,000 different tests, run all of them, I can guarantee that your microprocessor will be defect free if there is these tests pass. Then he'll say, no, sorry, thank you, it doesn't work like that. So defects are physical mechanisms, something going wrong in the manufacturing which is causing that defect to occur. We don't have the time to talk about defects. Instead, we talk about faults. Faults are the realization of the defect. Because of the defect, the circuit behaves as though a particular node is always 0 or always 1. So if you take an AND gate, and if you see that the output of the AND gate is always 0, there can be many reasons why it is like that. You have to go down to the level of the transistor. You can look at the transistor level layout of that AND gate, and then you may figure out what exactly is going wrong. Okay, many different defects may translate to one particular faulty behavior. So if somebody comes and says, oh, students are not paying attention in the class, right? That is a fault, right? They are not paying attention is a fault. Why are they not paying attention? There may be so many reasons. Maybe I am not teaching very well. Maybe my voice is not very audible. The internet is not good. Or, the subject matter is very dry. So many reasons could be there. Or they may be distracted by noise around. So we are not getting into that. We are only looking at faults. So the manufacturing tests only deal with faults. They cannot deal with defects because there are too many of them. Is that clear to everybody? What is the difference between a defect and a manufacturing fault? Manufacturing defect and a fault. Manufacturing defect is a dust particle or a impurity in silicon or two metal lines getting short circuited because of some manufacturing process not removing the metal properly and things like that. Okay. So if you go back to the analogy of that cookies and so on, maybe in some step the heat in the oven is too much or too little or something like that, because of which the cookies may be overdone or underdone or something like that. We will not be able to talk about all those defects, etc., when we do mass testing of the cookies. We are only interested in, are the cookies overdone? Maybe by looking at the cookie, the color, we can figure it out. If they are too brown, it's possibly not good. If they are too soft, it may not be good. So we have to look at these faults rather than defects. Is that clear? So in the same way, in manufacturing testing, we are only looking at faults, and we make a big list of faults that we want to test for. Okay. And if these faults don't exist, we will stamp the circuit and say it's good. And stuck at faults is one important fault model. That means every wire in the circuit we look at, and if we can convince ourselves that there is no wire in the circuit which is permanently stuck at 0 or stuck at 1, then that gives me a lot of confidence. Maybe this doesn't have that many defects. Okay. Can we say it is defect free? I don't know. There may still be some defects because of which these faults don't occur, but maybe there is some other fault which I am not modeling. Okay. So just like when the flight takes off, before the flight takes off, the engineers come and do some basic tests. Okay. See, they can't possibly go and look at every possible thing that can go wrong in the flight, right? They will look at a few important things, the engine and all those things. Right? There may be a few 10 things that they test. That is a fault model. If these faults don't exist, they assume that the flight is good to take off, because they don't have too much time. The flight comes, and within an hour or two, it takes off. So in that 1 hour, they have to refuel. They have to ask the engineers to certify that all is good, and then the flight has to take off. There is not enough time to start worrying about what are all the things that can go wrong, etc. Okay. So that is what a fault model is. We just make a small list of things and we just check. Okay, I hope you understood the difference between defects and faults. All right, so we ran out of time. So you can watch the lectures, and then if you have any doubts next week, you can ask. Okay. Any questions before we break?
No, sir.
No, sir.
All right. Well, I'll see you guys next week. Okay. Bye bye.
But sir,
Thank you, sir.
Any question?
sir,
No,
sir,
just-
graded assignments.
Yeah.
Hello. Sir, in our graded assignment, there were some questions in which I have multiple answers are correct, but only
Yes. Yeah. Correct. Good point. See, if there is a question like that, then if you mark all the correct, suppose A, B, C, D are there, and A and C are both correct. Then if you mark A and C correctly, if your answer is A and C, then you get full marks. If you say A, C and D, you get 0 marks. So if you select any wrong answer, you will get 0. If you select A only and not C, then you get 50% marks.
partial marks.
Okay,
But in
partial
our
marks.
graded assignment, it is marked as the single correct, not as the multiple choice. So there maybe some of the students have got the less marks.
I don't know about this, but check with Ashutosh. This is what is the policy. If A and C are both correct, and if you mark anything other than A and C, you get 0. If you mark only A or only C, then you will get partial marks.
Okay, sir.
Hello, sir.
If your grades, if you find that there was a grading error, you can contact Ashutosh. Yeah. What else?
Sir, can I ask from the lecture? One
Hmm.
topic I didn't understand. That's why.
Hmm.
So from the week 4 lecture 2, on the second example, you said that the D have changed to D bar. Why it happened exactly? There is no reason that you said in the lecture. That's why I'm asking.
Oh, I don't remember what that lecture is. Can you just
Lecture,
give?
yes, sir. Lecture was about D algorithm and PODEM problem solving.
Hmm.
So it's the second example that you showed. The fault was at the input A, and it was A is stuck at 0 volt, and stuck at zero means it will be D. But at that same point, there is a branch going around, and that branch it says that the D will be converted to D bar. So why is that happening?
Oh, I will have to check, man. I have no idea. Just do one thing. You talk to Ashutosh, and he will bring that to my attention. If
Okay,
there is
sir.
a genuine error that may see, sometimes while explaining, maybe I made a mistake. It's possible, right? A D cannot suddenly become a D bar if that is what you are asking. See, while
Yes, sir.
propagating, first thing is to activate the fault, right? At the time of activation, see, suppose you are trying to test for a stuck at zero fault. To activate the fault, you will place a 1. That causes a D to appear. And that D has to propagate further. If there is an inverter on the way, that D will become D bar. Okay. Just
Yes,
check
sir.
if that is happening in that circuit.
So
Along,
there
if a
is.
D propagates through a wire, it will remain D only. If it goes through an inverter or an AND gate of some kind, then it will become D bar.
Yes, sir. That's what happened in the previous lecture, that you did the same thing, but in the right way. But in the next lecture, in the lecture 2, the things got changed.
That may be an
That's
error.
why.
There may be an error. Just make sure that Ashutosh also or Ankita, one of them, has seen it. So maybe there is a genuine error there.
Okay, sir. Thank you, sir.
All right. Thank you. Anything else?
No, sir.
Okay. Bye.
Sir,
Sir is not there.
okay, okay, yeah.
But I guess Ashutosh is there. Means we can.
Like I have a general question. So in production testing, I mean, whatever the product we have manufactured is tested against the test cases. So if a product fails there, then how the companies are compensating those loss? Because they invested in design, manufacturing, testing, so every cost is involved there. After that, if a product fails, so I just want to know about how they are compensating those loss. That's all.
I guess that product will not be gets sold in the market because at a
Yeah.
time they are producing 10 to millions of millions of chips in at a one place. And if some of the chips are not
Yeah, so if they can't go into the, I mean, no go product, then so basically it's a loss for them, right? So I just want to know how will, I mean,